All right, today's quick hit video is going to be looking at probability. So we'll see a lot of probability questions. We probably use it even in our daily lives without realizing what we're doing. When we play sports or we play baseball, how many hits out of how many at bats, or free throw percentages and things like that. So we have probability in our everyday lives, but there's some different terms and some different um, events where we're going to calculate them differently. So we need to make sure that we understand whether something is independent or dependent and those different things. So one of the first things that you're going to deal with in working with probability is sample space. Sample space simply is just all the possible outcomes. So you'll see some test questions like this. Now, when we get down the road where we're talking about events where we have 20 different outcomes and we're doing it multiple times, drawing the sample space for something like that is going to become very time consuming and difficult to do. But let's say the sample space of flipping a coin and rolling the dice, or a numbered cube. Well, my coin toss can be heads or tails, and then the dice can be 1, 2, 3, 4, 5, or 6. Okay, it could have been tails on the first one, and that doesn't change. The roll of the dice can still be 1, 2, 3, 4, 5, or 6. So I have two possible outcomes on the coin. I have 6 faces of a dice, so 2 times 6 is where I get 12 possible outcomes. So you can write it like this. Again, this didn't take too long, but if we had, we're doing this 4 or 5 times, or had other things that we were adding in, we'd be drawing branches and branches and branches. It would get very messy and become very time consuming. So sample space is just all possible outcomes. If we're talking about something where we have, you're going to end up with thousands of possible different outcomes, we're not going to be drawing anything out like that. But flipping a coin 2 or 3 times, rolling a dice, something like that, we can do that. We could also write it as heads 1, heads 2, heads 3, heads 4, 5, 6, and tails 1, 2, 3, 4, 5, 6. I prefer this method just because visually it makes more sense to me, and I can see, okay, heads or 1, heads or a 2, heads or a 3, and so on. This way it works. It's just for me, I know I got all of the possible events accounted for when I do it this way. But that is just sample space. Now, probability itself, it's just the likelihood, the chance, the odds. We sometimes refer to it as a few different things. It's just the likelihood that something is going to happen. Now, that range is from 0 to 1. If it's halfway between, it's what sometimes we call 50-50. We flip a coin. It's either heads or tails. It's 50-50. So there's a half of a chance that it's going to be heads, half of a chance that it's going to be tails. But if it's impossible that it's going to happen, it's going to be 0. And as it gets closer to 0, it's the likelihood of it happening is less and less. So like hitting the lottery, it's not 0, it's not impossible, but it's going to be somewhere very close to 0. Now, something that's certain to happen, that's going to be a 1. Like you wake up in the morning and it's either cloudy or the sky is clear. Well, it's going to be cloudy or the sky is going to be cleared. It's obviously going to be one of those, so the probability of that happening is absolute. Or the sun coming up, or just something that we absolutely know 100% is going to happen. Like we flip a coin and we land on either heads or tails. Well, it's got to land on heads or tails, so it's a 100% chance that it's going to land on one of those. So we can express probability as fraction. Okay, we can do it as a decimal or as a percent. Fraction and decimal between 0 and 1%. Okay, 1 that number expressed as a percent is 100%. So we can't go over 100% chance. So You probably have heard probability when referring to the weather. Oh, tomorrow, watch out, there's an 80% chance of rain. Well, that means there's a 20% chance that it's not going to rain. It's either going to rain or not rain. There's only two options. It's got to add up to 100%. So that's an event. And then its complement is the opposite of that. So 80% chance of rain. The complement to that is not raining. So that's a 20% chance in that example. But it's got to add up to 1, or percentage-wise, it's got to add up to 100%. So that's probably, if you ever get a probability that's like, I was just working with a student and they flipped their probability and got 3 out of 2. Well, they can't have a 3 halves chance of something happening. That's 1 and 1/2. That's greater than 1. It can't be more than 100% certain. So if you ever get a probability that's a negative, it's never negative. Even if it's a 1 in a trillion chance, that's still a positive number. It's just a really, really, really small number. So again, 0 to 1, if it's half or above, or 50% or above, we say it's likely going to happen. If it's below that, we say it's unlikely to happen. And the closer it gets to 1, the more likely. The closer it gets to 0, the more unlikely. Okay, then when we're working with probability, we have theoretical versus experimental. So theoretically, I flip a coin 10 times, I should get heads 5 times and tails 5 times. But in the actual experiment, I may get heads only 3 times and tails 7 times. That doesn't mean that the probability is false or anything like that. It's just for the actual experiment. Here's how it worked out to be. Now, over time, if you just do 1 or 10, once you get to 100 or 1,000 or 1,000,000 of those, you're going to get closer to this probability. So you flip a coin 10 times, it might be 3 to 7. 100, it might be 55 to 45. You do it 1,000,000 times, it's going to be very close to 50-50, or half on one and half on the other. So that's theoretical. The more you do experimental, the more times you try it, whatever it is that you're looking at, you're going to get closer to that theoretical probability. But that's experimental versus theoretical. So you may be pulling people and only 20% in the area are Raiders fans, but you may go up to 10 people and you may coincidentally get 10 people in a row that are Raiders fans. That doesn't mean 100% of people are Raiders fans. It's just happened for your experiment and your sample size. That's what you got. Okay, so experimental versus theoretical. Okay, an event and its complement. So P of A, the probability of event A. Sometimes we refer to them as event 1 or 2. A lot of times it's event A and B. We refer to that. So probability of A and probability of not A, that's what we call the complement. And an event and its complement always add up to 1. So back to the example of 80% chance of rain. Event A is probability of rain, and it's 80%. That means there's a 20% chance, the complement, of not raining, and that obviously adds up to 100%. Okay, so an event and its complement always add up to 1, or 100%. Now when we're trying to calculate multiple events, we could draw out the sample space and find where do we, in this example, rolling a dice, we land on a 6, and then we flip a coin and we land on heads. We could do our sample space 1, 2, 3, 4, 5, 6, and then 1 heads, 1 tails, 2 heads, 2 tails, and all of that, and find it. Nothing wrong with that, besides it's going to become really time consuming. And then what if we flip the coin 5 times? Okay, we want to have a quicker way to calculate this. So first, let's find the probability. We'll call this event A. We're going to multiply that by the probability of event B, and that's going to give us the probability of event A and B. All right, so 6 on a dice. Well, there's only 1 6, and there's 6 options, so I have a 1 in 6 chance of that happening. Heads or tails? Heads, I have a 1 in 2 chance of that. Now to get the probability of A and B, I just multiply probability of A times probability of B, which gives me 1 12th. There's a 1 in 12 chance. So instead of writing out all the possible options and then circling this one, this is a little bit easier and quicker way to come about that. Now, these are independent events because rolling the dice has no effect on flipping the coin. If this landed on 1, 2, 3, 4, 5, 6, that has no effect whatsoever on the coin. Whereas we do have probabilities where we have dependent events. So let's look at a deck of cards. Now, if you don't know, a deck of cards has 52 cards. So if you don't know that, I know we see a lot of questions in the book, and sometimes it gives it to you, but usually it assumes that. So let's talk about it now so that way we've at least covered it. So there's 52 cards in a standard deck of cards. So let's say the probability of picking a king. We have 4 suits, so I have 4 kings, so 4 of the 52. So my first king, I have a 4 in 52, or that could reduce down to a 1 in 13 chance of picking a king. But now I've taken one of those 4 kings away because I'm not, if it says I take it out, look at it, put it back in and replace it and reshuffle and do all that, then draw again, then it's independent. But if I'm drawing 2 at the same time, or 1, keeping it out and then drawing the second one, doesn't matter if they're at the same time or one then the other. If I kept that first one out, now it's a dependent event because I don't have 52 cards anymore. I have 51 cards because I pulled one out and kept it out. Okay, if that first one is a king, I no longer have 4 kings. I have 3. Okay, and 3, as I reduce down to 1/17. So now the probability of drawing 2 kings at the same time, or 1, keeping it out, and then drawing the second one is 1 in 13, not 1 in 13 times 1 in 13, 1/13 times 1/17, which gives me 1/221. Okay, so read the problem carefully. Does it say I'm taking something out and replacing it, putting it back in, or am I taking something out and keeping it out? Because that changes the probabilities. One of those situations is independent events, and it just multiply 1 in 13 times 1 in 13. But if we're, in this example, we're not replacing it, then they're dependent events. This second probability is dependent upon what happened in this first event. Okay, let's say we have 2 white marbles in a bag of 6. Okay, what's the probability or chance of drawing them both? Well, the first marble, I have a 2 and 6, or reduced down to 1 in 3 chance, but now I no longer have 6 marbles. I have 5. I don't have 2 white marbles in there. I just have 1 left. So I have a 1 in 15 chance of that happening. So read the problem. Is it an independent event? Probability of event A and B, are they independent? Or probability of event A and B, are they dependent? That's going to affect your probability. So just pay attention to that. So again, probabilities, we have sample space, theoretical versus experimental. And then we remember that probability is always between 0 and 1. Impossible, absolutely going to happen no matter what. Okay? And then a range between there. Right in the middle, to the right of that, it's more likely to happen. To the left of it, closer to 0, it's not a good chance of it happening.